are certainly exceptions. There's sort of several ways we could do this, and probably what I'll try to do, unless I hear otherwise, is a couple different things. So I wanted to start by doing very basic preliminary stuff, just sort of walking you through firing up Python, assigning variables, discussing data types, that kind of stuff. And this is not meant to be super tutorialist, because I imagine how many of you are familiar with the idea of data types? Or if I tell you, a string and a float, how many people are familiar with that? That's not, okay. So most of you. So I just kind of want to breeze through that, mainly for people who kind of have done some programming before, but maybe want to see how it's done in Python. But I won't really spend very much time. So maybe we'll do half an hour of just very basic stuff in Python, so you can see the Python take on common programming things. And then we kind of have two options. We could either spend some time just doing demos and sort of on the fly, playing around with some of the major sort of data sciencey packages like Numpy and Pandas. Or I could talk a little bit about the sort of pros and cons of Python in relation to other languages like MATLAB and R. Any particular preference? I mean, do people want more of a sort of like a lecture, or do you want just a hands-on demo? You can ask questions. Either one is totally fine with me. Okay. And then the other thing I'll say, and I'm glad you brought that up. So last year, I actually did several different, so we're trying something a little different this year. Last year, I did on day one several different, there was a visualization in Python one, there was Python tips and tricks, and then there was a data wrangling in Python. And this is actually none of those. This is sort of meant to be just core Python. But I'm happy to kind of redo any of these during the week. So if there's enough interest, like I'm talking like 4 or 5 people, not like then I'm happy to sort of take a room for the breakout session and go through any of these things. So if you really want to know visualization or data wrangling Pandas, then that's cool. I'll talk a little bit about Pandas today probably, but I wasn't planning to spend a lot of time on it, unless everybody wants to talk about Pandas, in which case we can just do that now. So so this really depends on you guys. Yeah.
Are these notebooks available?
Yes. So these are if you go to last year's. Actually, if you go to the organization, oh, sorry, you can't see that. If you go to this, so github.com/Neurohackweek, there's tons and tons of pretty much everything from last year is on there, to the point where it's actually a little bit confusing. We probably should reorganize that. But so yeah, data wrangling Pandas. That one I did a lot sort of on the fly, so there's actually not as much content in there as the video is also online, so you can also watch that. There's the Python tips and tricks. There's all kinds of other things. Python, which I don't think we're going to do this year, but all kinds of interesting stuff. So yeah, you're certainly welcome to work through those, and then come find us, or we can talk about it now. But let me just start off with, I think, the very basics. And so, how many people have Python installed? Hopefully, everyone. Okay, good. So one way to tell is that if you whatever platform you happen to be working on, if you fire up a command prompt or a terminal or shell or whatever is appropriate in your system, and you type Python, that should drop you into a Python shell. Okay. That'll work for everyone? Does anyone not have Python do something when you type Python in there? Okay. So all right. So can you read that? Okay. Okay, so this is a Python shell, right? Python, as some of you may know, is an interpreted language. So what does that mean? Anybody want to provide a? Okay, so it's not compiled, meaning. Yeah, so when you run a Python script, right, it's just a plain text file essentially, and you have a interpreter, which is just a program that knows how to read Python, and it just goes line by line through it. So it is reading much like you would, and it just executes line after line, figures out what to do on the fly. And that's contrasted with compiled languages where the entire code base, whether it's one file or multiple files, is first turned into some form of machine code or some other binary that some other system can read. And the trade-off is that when you have a compiled language, because you can generate this sort of low-level, machine-readable thing, you get to do all kinds of optimization. You can catch errors. So you can do all kinds of checks and make sure that things look like they're supposed to, that variables are getting passed in where they are, et cetera. The benefit of interpreted language is, on the other hand, it just starts executing right away, right? And so the trade-off, there's lots of different things, ways to characterize it, but broadly speaking, you think of this as sort of speed versus speed of execution versus flexibility, right? So if you have a language like C or Java, those languages tend to be very fast. They're relatively close to the metal, but developing them takes more time because you're doing a lot of things explicitly that you would do that you wouldn't have to do at all in Python, or that are implicit. And with an interpreted language, conversely, the main cost is that you may start running that script and it works fine for 6 lines, and then there's an error, but the syntax is okay, but there's an error in the code that doesn't get caught until the thing is running, and so you have lots and lots of runtime errors. And it also tends to be slower because there's less optimization. So Python is an interpreted language, which means that basically you can essentially interact with the interpreter in real time. And so you can start once you're in a Python environment, you can of course start typing. So you can assign a value to a variable, you can print variables, etc. And all you're doing here is you're essentially talking to the interpreter. You're sending it lines, and it executes them right away. There's no delay. However, this is not usually the way you want to write code. This is great if you're doing data analysis, right? So if you're used to R, for instance, most people will at least start looking at their data just by dropping into an R prompt and just looking at the data sort of line by line and executing functions. But generally speaking, once you want to actually sort of write a piece of code that will run on potentially multiple data sets, or you can send someone, rerun later, you're not going to want to do this sort of piecemeal line-by-line thing. You're going to want to actually put your code somewhere, like in a file or something. And of course, you can open up a flat file. We could do that, but I think that's probably beside the point. You all know how to open a file and save a file. Instead of working with files, what we'll do today is work with Jupyter Notebooks, and you've probably already seen them in other tutorials. How many people have worked in the Jupyter Notebook before? Okay, so most of you. For those people who haven't worked in Jupyter Notebook, in theory, again, if you've installed everything per the instructions for the course, so if we just quit out of this, then it should be the case that if you type Jupyter Notebook and run that, you will get something popping up that looks like this. So if you are able to do that, if you can get a Jupyter Notebook running, it doesn't really matter where. We're just going to sort of experiment on the fly. We're not going to use any pre-baked notebook for now. Is everyone able to get something like this up and running? If not, let me know, because you can go to the Neurohackweek Jupyter Hub installation that's set up. And so that's another approach. As I already showed you, you could just navigate there, and you would get something like this, and you can start playing around right away. What we're going to want to do in this case is you can create, if you haven't already, a new Python 3 notebook, and that'll pop up something that looks like this. And this is a Jupyter Notebook. And I won't say any more about it than that because, as you probably saw in the schedule, there was a Jupyter session right before this. And so if there are specific questions as I'm going through, let me know. But otherwise, I'll just assume you kind of already know roughly at least how to use this thing. And for our purposes, we're not going to play with any fancy features. We're just going to write Python code and execute it. And so the nice thing about Jupyter Notebook is it's sort of intermediate between having one big script or code base that you can run sort of in one shot and having that sort of interactive environment where you can run things line by line. So you can write codes or blocks of text rather than just a line, and you can execute them as you like. So let me just pull something else up here. Oops. All right. Okay. So Python is a very deeply object-oriented language, and I'm not going to talk about what exactly object-oriented programming is. The only kind of reason I'm making that point is that everything in Python is an object. So it's a thing, right? If object seems like fairly abstract, just think of it as a thing, right? Everything, not just numbers and strings, but in fact even functions in Python are objects. They're just things that sit there and can do certain things if you ask them to do, if you ask them to. And so, of course, at the simplest level, you can think of like a number. So here's a number, 4. Okay, and if you run that cell, so just type either hit sort of run here or just shift enter as a keyboard shortcut, then the Jupyter Notebook by default will do what the Python interactive shell does, which it'll just echo back to you whatever the evaluation of that thing is. And so if you evaluate 4, it evaluates to 4, and it prints that right back for you. So no surprises there. If you were to do something like a equals 4, right? So you just assign a variable, or equals 5, then you don't get anything back because there's nothing echoed to the shell. That doesn't return anything. So you might think of this 5 as just a number, and it is. But like any object in Python, and if you ever really want to know what anything does, including a number, you can use this dir function, which will actually show you all the secret stuff that's actually going on. So this is actually, a number itself is actually an object, has a class. It's a kind of object, it's an integer. And like all objects, literally every object in Python will show you all of this stuff, right? And don't worry about it, we may or may not get to it. These are all what's called magic methods with the double underscores. You will probably not have to work with these very much at all. But if you scroll down, you can see down here that it has this stuff. It doesn't have these underscores. And these are now attributes that are defined on that number, right? So these are actually properties, they're things the number can do. And any number will be able to do these things. So I'm showing you that only just to kind of give you a sense that even though superficially this just looks like it literally is just a number, nothing else, everything in Python, right down to integers, is actually an object. There's more stuff it can do than just be a number and have a value. Now, of course, like any Python object, we can do things like printing this number, which will just print it back. It's not terribly surprising. We can, of course, move from numbers to strings. And so in terms of basic data types, you have integers, you have floats in Python. You have, of course, strings. So if we just create a little string called hello world. And we have our string assigned. And the same principle applies here. If you ever actually want to know what this string can actually do, you can see there's a lot more stuff that strings do than integers. And each of these things are attributes, generally they're methods that can be called on these things. So you can think of them as essentially sort of abilities that the object, in this case a string, has. Now, one difference between Python and other languages, for example R is very much a functional language, which is to say almost every time almost everywhere you're interacting with data in R, you are typically calling functions, right? So you'll very often be doing in R things like reshape. And then, of course, there's one where this is not R code, but you'll be doing things like reshape data, or it's been a long time since I wrote any code in R. But almost everything in R, because it's a functional language, involves having a function that you just pass in variables to as arguments. Python certainly has built-in functions. So, for example, len is a built-in function that tells you the length of an object that has multiple elements, an iterable it's called. So if you have something like this, anyone know what this object is called with the square brackets? Yeah, it's a list in Python, which is essentially equivalent to like a vector in R or an array in many other languages, right? It's just the simplest ordered container of things. It can contain any number of objects. They do not have to be of the same type. So, sorry, just to.
Would you mind increasing the font size a little?
Yes, sure. Sorry about that. Better? Maybe that's too much, maybe. Okay. Does that work? Still? Okay. Right. So let's say we have a list. We can have mixed types. That's not a problem at all. Right. So there's no requirement that lists have homogeneous type. And so that's an object we define, and then we can call this len function, which expects certain kinds of objects, of which a list is one, as input. And just like in other languages, it will not surprise you that this thing basically just tells you the number of elements with the length of the list. So there's 3 things in there. Okay. Where's mine? Okay. Now, you can't arbitrarily take any function and apply it to any input. Again, this makes sense if you're coming at this from some other language. But suppose we have that HW thing, right? What happens if I type len of HW? Any ideas? Okay, it's going to count the number of characters. Yes, right. So there's 12 letters in that. Okay. But if I had an object that doesn't take a length, and actually I don't know if that's true of any of the core data types. Actually, I think a number, for example, right? You cannot take the length of a number because a number does not, it just has a value, it does not have multiple elements. A string in Python is defined so that if you ask for its length, that's interpreted as you wanting to know how many characters there are, but that does not make any sense for an integer. This also kind of underscores one of the things many people don't like about languages like R, for that matter, Python for that matter R, which is that they have what's called duck typing. Does anyone know what duck typing is, or dynamic typing? So the idea here is that when you initialize a variable, you don't actually specify what the type of that variable is, right? So you'll notice that when I do that HW equals hello world, I'm not saying that's a string. That's just implicit. When you assign the string to that variable, it's now a string. What that means is when you look at a variable somewhere in your program, you don't actually know the type. And worse, there's no guarantee that when you execute that program, you will have a value of the type you expect. Right? So you might write some code that always expects a string everywhere. You think HW always has to be a string. But somewhere in your program, someone could easily say, look, I'm now going to set HW to 4. And, right, so, and then you, somewhere else in your code, maybe have some code that's trying to convert that string to lowercase. So you have this. This is a method that expects a string and operates on strings and converts to lowercase. But it won't work now because someone has turned into an integer, right? So this is one of the downsides of Python is that you don't have static typing. When you create a variable, you don't declare ahead of time what the type is forever. And something to be aware of is that, I mean, this is nice because it makes code readable. It's less characters to type. It makes it much more flexible. But there is a cost, which is that it's in some ways much easier to make certain errors. Another kind of problem, this is where I was getting to earlier, is that every type of object defines what you can do with it, right? So integer, well, you can divide an integer, but you can't divide a string. And so you can think of this as every type of object having different kinds of abilities, and figuring out what objects can do what is part of what is entailed in learning a language, right? You're basically just learning what things you can do with strings, what things you can do with integers, etc. in part. And we have strings, we have integers, we have floats. We also have Boolean values, which some of you will know, right? So are true. There are only two values, right? True and false. So a Boolean variable can be either true or false. And a very common and important thing you do in programming is evaluate expressions that evaluate to one of these things. So often you want to know if some condition holds. And so if we have our HW variable we just defined there, and we want to know, maybe we have some program that requires text input, but it can only be text of below a certain length. If it's too long, then bad things will happen. So we want to make sure somewhere in our code that HW does not have more than 6 characters. Essentially, so we can evaluate this expression. And so if you just write this expression, length of HW is greater than 6, what is that going to evaluate to? It's going to be true, right? There's more than, oops. Oh, see, right there. That's your duck typing problem. So we'll get rid of this just so it's less confusing. And we will, X. So the notebook has 2 modes. So when you're in edit mode inside a cell, it's sort of just typing, but if you hit escape or if you click outside, then you're operating on cells, and then you have shortcuts available, like you can copy, paste, etc. If you want to know what those are, you just go to keyboard shortcuts, and that'll show you both for command mode and edit mode. It's very easy to accidentally delete cells. You can undelete them, but it's a little buggy, so be careful. Anyway, so we ran our HW, so now we have a string again, and now if we evaluate that, it's true because it's more than 6 characters. I'm probably going too slow, right? This is sort of old news to people. Okay, I'll pick up the pace a little bit. All right. So, okay, you've got data types, you've got functions. One thing I will mention, I've already kind of touched on this. In Python, functions are also actually objects. So here's how you define a function in Python. Let's say let's call this double. So we write a little function that doubles the value of whatever you give it. That's all it does. Okay. And so if we run that, now we have, now we have this function. And again, if you're coming from some other language, you might think of a function as purely the sort of abstract thing that does stuff when you hand it stuff. But actually, functions in Python are objects too. If you just type double here, it'll show you that it's just a thing. And once again, you could, if you want to know what the function does, although this will not be really, this will not be super useful very often. I should probably double my screen, but there you have it. So everything is an object, including functions. I may come back to this later, depending on how things go. So Python has built into it some functions, but not a lot. In fact, if you go and look at the built-in, so if you just Google Python built-ins, it turns out that the number of functions you have available out of the box is pretty small compared to languages like MATLAB or R, right, where you often have like literally hundreds, if not thousands, of functions you can call. That's by design. There's not all the functionality that's in Python, but Python takes a different philosophy than some other languages, especially a lot of other dynamic, sort of high-level languages, in that it basically forces you to be explicit about what it is that you want to do. And a lot of its functionality is locked up in what are called modules. So you have, of course, lots of packages that other people write, but even in just the base Python distribution, the standard library, there's lots of functionality available to you, but you don't get to see it unless you explicitly say, I want to use this chunk of code from somewhere else in the library. And so, for example, how many people are familiar with regular expressions? Okay, a few of you. So regular expressions are a really nice tool for manipulating and extracting information from strings. So, and in fact, if you haven't seen regular expressions, I'll show you a little bit here. But really, I would encourage you to look them up, because no matter what language you're working in, they will change your life if you have to work with large strings. And the idea is that you are basically pattern matching, right? So let's say you have some chunk of text, and somewhere in there you know that you need to look for the values that shows up after the text name, right? So maybe you're trying to pull a name out of something. Well, you could do that with string operations. You could take that text and say, well, I'm going to look line by line, and I'm going to scan every character until I see one that starts with the name, and then I'm going to take that chunk of information. Or you could just say, here's a little pattern that defines exactly what I'm looking for, apply it to the string, and give me back the values. I'll show you an example. But you don't get that for free, and you do in some other languages. You have to explicitly import that. So in this case, it's very simple. You have this regular expression or RE module in Python. It comes with Python. And so if you just run that, nothing happens, but you now can actually access regular expression functions. And if you, in Jupyter Notebook, hit dot after the module and tab, it will show you all the possible completions. So these are all things that you've now gained access to just in virtue of importing. Now, why do this? Why make the imports explicit? Because if you don't, and again, depending on what language you work in, this may run into this, it's very, very easy to import or to basically have packages that you reuse the same names. And so you end up in a situation where like 6 packages all want to use the name mask or something, or apply, and then you don't actually know what you're getting. And it's also very hard to know where it came from. So you see like in a long script the word apply somewhere, and that's not a good example because it's in base R, but you know this thing came from some external package, but you don't know where. In Python, generally these are put at the top of the page, so you can always scroll up and see, yes, that's where this function I don't recognize is coming from, and I know exactly what it's doing. Okay, so in this case, we've imported from RE, and so now let's say we want to search within our HW string we just defined here for the 2 characters preceded by W, right? So again, this would be a pretty odd or a pretty difficult thing to do with sort of standard string operations. So how would you implement that, right? You might say, well, I have to go through character by character, I have to loop over those characters, I stop when I find a W, and then I count the next 2. That's a lot of work. Here's a simpler way to do it. We say, here's our pattern. We are looking for, and this is now it's basically like a specialized little language for working with strings. And so we say, we want to find a W, and what we actually want are any 2 characters following that. Okay, and again, this is, there's just special syntax you learn. It's not like obvious at a glance what it's doing. And now if we search through, or search for that pattern in that string, we get some result. It's also an object, so let's store that. We can call this our matches object. And a matches object happens to have this groups property that just gives you all the matches. There could be more, but in this case there's only one. But notice, right, that instead of having to do all sorts of complicated things, we just basically said, here's the pattern we want to match in the text. The parentheses indicate what we actually want to catch. So we're saying the W is outside. So we're just saying look for a W and then keep the two characters, the dot stands for any character, right after that. And so or is indeed what we're looking for. Okay. So this was really just meant to show you that there's lots of functionality sort of tucked away that you wouldn't know about if you just look at the sort of 60-odd functions available out of the box. But there's lots and lots of tools in the standard library.
Do you have to re-import every time you need to use it?
No, that's a great question. No, so you only have to import once at the beginning of the file, or in this case, at the beginning of the notebook. Now, one small gotcha you may run into, although you probably won't, is you can't actually very easily unload a module. There are not many cases where you want to unload a module, but if you do, you have to do a little bit of hacking. It's not the easiest thing in the world, so be aware of that. But importing is very straightforward. You just import whatever you want. There's several different conventions for this. So maybe you don't want to import into your namespace all of regular expression module. Or maybe, look, all I want is to search. And I don't want to deal with this long having to type like re.search. Maybe I use search over and over. I just want to call that search. I know what that is. Fair enough. What you can do is you can import from. So you can say from re import search. And so now you have in your namespace search. And so search now is valid, right? And so again, you can see how this could be useful because it gives you a lot of control over exactly what variables are named what. And you can also, if you want, maybe search is confusing. You don't want to call it search because that might conflict with something else. So you can say import that as re_search. And so now that re_search variable maps onto that module. Oops. So you could now do the exact same thing as before, called on that variable, if that makes sense. To some degree, knowing Python, this is true of any language, when people often say, I know Python well, often what that really means is, I know all the tools that are available in Python, right? And in general, if someone else has written a package that does what you want, most of the time, it's probably in your best interest to use it instead of writing your own code. And so a lot of what knowing a language well amounts to actually just ends up being knowing what tools are available for you so that you don't have to do a lot of work. And so it's a good exercise, quite frankly, to just fire up once in a while the list of modules, and this would be in Python, but obviously in other things too, in the standard library. And just look at it, because there's all kinds of stuff it provides for you. Again, you would have to import from it. But there's lots and lots of functionality there that you probably won't be aware of if you were just sort of even just looking at other people's code. It's helpful to just go through this sometimes. And a lot of this will not make any sense to you if you haven't done much programming before. But some of it will. You might, for example, see, oh, there's a JSON module. That's good. I can use that to read JSON files. I don't have to write my own parser that figures out what the structure is. So you can actually short circuit, in some sense, the process of becoming proficient in Python or other language just by knowing what's available. Often you can use someone else's really good tool, and then you don't have to be very clever or algorithmic about it. You can just find the thing that works best that someone else has written. Okay. Let's see. So for the purposes of comparison, so I mentioned already some of the core data types. Python has sort of, I would say, 7 or 8 core data types. And you can distinguish them in general by what they look like when you assign them. Right? So you will not necessarily know just that a variable exists. You won't know what its type is unless you inspect it. But you will generally, at least in assignment, know. So there's an integer, right, or int. That's a float. We've seen a string. We've seen lists, which again can have arbitrary type, right? So these are all different, but we can easily assign them to a list. We also have dictionaries. These are similar to associative arrays in JavaScript, objects, depending on what other language you're using. And so dictionaries are basically key value pairs. Again, very basic data type used almost in every language. Super important. So they have keys, and then you assign those keys values. So you can say, name, Sue, age, 51, and so on. And so now you can access the values in that dictionary by key, right? And so the convention here is you have this sort of notation. So when you want the value of a particular key in that dictionary, in this case, let's say you want the name stored inside this E dictionary, that would be how you get it. And so what you get back is the value. There are all kinds of helpers for dictionaries. So again, if you ever want to know what can this dictionary actually do, then you can look inside it, and you'll see that you have these things like values and keys. Those are probably the most common things you'll work with. So if you ever have a dictionary and you want to get all of its keys, for example, at once, then you can just do e.keys, and you will get back. This is actually its own little object, but really you can treat it as a list where you have name and age, right? So you're getting just the keys, and you could do the same thing for values. And that would give you just the same values. Dictionary is a very, very flexible structure. It's incredibly useful for all kinds of things, particularly because you can easily grab both the keys and the values. And so often, if you need to associate, maybe you have a list, but there's some other information you want to associate it with, it's helpful to store it as a dictionary because you can always grab just the values, just the keys, or the mapping. I think as of Python 3.3 or 4, maybe actually later, all dictionaries are ordered, which means that in addition, so historically dictionaries were not ordered, meaning you could guarantee that the key name would be associated with the value Sue, but it didn't have any constant order. You couldn't say give me the first pair in that dictionary, right? You could not guarantee that the order you put them in is the order they come out of. That has changed, I believe, but there is still implicitly an ordered dictionary object if you want it. And as I just said a moment ago, in general, there are more useful data structures in the collections module. So a very commonly used module is this collections one. Has all kinds of useful things. It also has something called the default dictionary, which I find incredibly useful. Typically, if you I'll show you an example. Right, so if I do something like, let's say I have an animals dictionary, and then I see a dog, and let's say this is supposed to be a counter. It's just keeping track of like how many animals of each type I see, and I see a dog, and I want to say, oh, I saw another dog. So it's intuitive to want to do something like this, because I'm implicitly thinking, well, the value of dog is 0. This will not work though, because I haven't actually assigned that key, right? So what I would have to do is first say this, and then when I see one, then I could then do, right, and that works fine. Default dictionary is basically a way of creating a dictionary where you tell it, if there's no value already set, give it a default. And it just saves you from having to create this extra line, which in practice often means that when you observe a new key, you first have to check if it's already in there, and if it's not in there, then you create the key. And so this kind of is just a little convenience for getting around that. And so you can say default dict of int, and that argument to default dict is the type that's supposed to be set if nothing is present, and that is going to be the value 0 because it's the default integer. And so now next time I see a cat, I can say, maybe I see 2 cats, so I want to increment my count, and that'll work fine now. And if I then look at my default dictionary, which behaves just like a normal dictionary, you can see that I still have that data, right? So again, just making the point that there's lots more data structures beyond what's just given to you, and oftentimes you won't have to write your own. This is very, very common where you think, well, I need this thing that behaves kind of like a dictionary, but I also need to do this other thing, like I need to maintain order, or I need to have default value. Go look in collections or elsewhere in the standard library, because you will often find that someone else has done the hard work for you, basically. All kinds of interesting containers. Most of these I have no idea what they do. I mean, there's just so much in the standard library that, like, I've probably used maybe like 5 or 6 of these in my life, right? But I'm sure they're all useful to someone depending on what they're doing. Do we need to talk about control structures, for loops, if, then, conditionals, or people like okay with for loops? I'm fine. I'm happy to talk about them, and we want to make sure that everyone feels like they're sort of getting what they need out of this. So, okay, I'll assume I'll assume that you understand for loops and conditionals and so on. I'll just show you what they look like. So one nice thing about Python, one thing people like in general is it's fairly readable. And you may have already noticed this if you've sort of looked at code. Even if you don't really understand it, it looks more like something a human might read or write than many other languages. And that is true even at the level of the operators, right? So when you want to loop over something, you actually are using the words for, in, and so, for example, we have our list up there. We made here this list D that contains a bunch of other objects. So we can say for element in D, and so it's very human-like. You're saying like for everything in this container, take it and do something else, and then if you could say if this element what would make sense to apply here? We can ask if this element is a string, or actually an integer, for example, and it's larger than 2, right, and so So in this case, we're just looping over our little list there. And for every element, we're checking if it's an int. This is the way you do this in Python. There's other ways, but this is probably the safest. And then if it is an integer, then you're asking, well, is it bigger than 2? Right? And so you can see that this is sort of, it's fairly easy to understand what's going on here. Again, maybe not this is instance thing, because you'd have to look that up if you're not familiar with it. But the general logic is pretty simple to understand, and a lot of it is sort of natural language-like. That's true for lots of other things in the language. However, you don't have to, if you really have an objection, like a deep-seated hatred of the word and, you probably find it very difficult to talk in English if you do, but you could use the and operator, right? So that does exist. All right, okay. The only other thing that's sort of really basic that I will mention, because it's important just in case you haven't seen it, is functions. I mean, I already showed you really quickly how to define a function, but
I used the and operator and gave me an error saying unsupported operand for Boolean export.
Oh, interesting. That is interesting because. So the reason is, yeah. So I think the Boolean might evaluate. Let's see. Oh, sorry. Yeah, okay. I take that back. The semantics are apparently different, right? So what's happening is that and implicitly converts. This is a Boolean, so it's either true or false, and that's. Wait, no, that's not right. Oh, okay. You're right. Sorry. It's just the It is literally just the parentheses. Sorry, my bad. So the no. Interesting. Okay, so I learned something about and. I'm actually not sure what the exact semantics of and are. Maybe it's a short circuit operator. Let's see. No, that's not even legal. All right, I don't know. So somebody can go look into that and get back to me, and I'd actually be happy to know. All right. Okay. Let's talk really quickly about functions. So I mentioned that functions are actually objects, but the only point of the most important thing about functions, right, is they provide you some way to abstract a chunk of code. And so it would kind of suck if every time you need to do something with your data, you have to write like basically just like statement after statement of code, and you could never use a chunk. Like if you wanted to do the same thing over again, you'd have to like type it out all out again, right? So all a function is, in the simplest case, is just a way of abstracting away a chunk of code and making it reusable. So we have some function, it takes an input, and maybe it just notifies you that it's received it, right? This is quite a useless function, but that's all right. Oops. And so now anywhere in your code that you need that, you could do all kinds of stuff. You could call this with any value you want, really. We probably want to print this, actually. Oops. So this is, again, fairly trivial, but the point is you have now modularized this and you've basically abstracted away the idea that instead of having to sort of hard code the values you want this operation to work on, you can take an argument now, right? And again, I know that you guys are probably all familiar with arguments and functions, but just wanted to quickly kind of touch on that in case you are not. All right. It's kind of hard for me to know what, depending on what language you're used to working in, what people find unusual or unintuitive about Python. So I want to move on to like talking about data stuff like Numpy and Pandas and so on, but I do want to make sure that like you have a kind of a clear idea of sort of the basics of Python, at least kind of like what the language looks like. Any questions? Like, what do you find odd about Python when you've tried to play with it, or that seems strange, or just doesn't fit with how you think about programming, maybe coming from MATLAB or R or Java or whatever? Any questions? Or is it really so super intuitive and obvious? Yeah.
So if you're using Python, I didn't know already, but what I still find difficult compared to MATLAB is that your error messaging, I'm like, really, like, can you not make the error messaging a little bit more intuitive? That I find much easier in MATLAB.
Yeah, and that's unfortunate. It's true. I mean, part of that is a lot of, depending on what you're using, I think a lot of the authors of some of the widely used packages are not very good at providing informative errors. So that's part of it. Another part of it, though, is that because Python is a very domain general language, it's much harder than with MATLAB to anticipate how people are actually going to use these tools. And so there's much less flexibility to kind of give an informative error because you don't actually know. And so what you're getting in some sense is a very literal explanation of what went wrong just before that line ran. And to try to give you any more would really be context dependent. And I've been in situations where I've kind of thought, well, do I write a very specific error message? But then you immediately think, well, no, because the same chunk of code could actually do something else. And then the user would be looking at this saying, like, I don't know what this means. It's not exactly, So you're right, but it's not clear that there's anything to do. What does happen, though, you'll find with any language, in fact, it wouldn't surprise me if someone who's worked in Python all their life started using MATLAB and say, well, I don't know, I just don't find these errors understandable, because a lot of it is just you see the same errors over and over and you learn, oh, that's what that error means, even if it's not super intuitive. With Pandas, this happens all the time, right? So there's just like 4 or 5 errors that you just get used to, and when you see it, you're like, oh yes, it's another one of those indexing errors, I know how to fix that. And even though it's not obvious from first principles when you look at it what it actually means. One nice thing related to that about Python is because it's such a widely used language, I think it's by far the most widely used sort of high-level dynamic language. Finding help is much, much easier than with something like MATLAB. I mean, you're almost guaranteed if you just Google, almost any error, any exception that comes out of a package like Numpy or Pandas, you probably will find like 50 hits for it. So there's that. But yeah, you're right. I mean, that's a problem. All right. Okay, so, all right, let's talk a little bit about numerical stuff. Let's see how we're doing on time. So what I'll probably do actually maybe is switch over to this, let's see.
Just like a small comment, why it fails in the and or and. They're sort of different, but the error is actually from the comparison, the a greater than 2, because it short circuits if it's not an and with the and, and the ampersand doesn't short circuit. That's where the error actually comes from.
Okay.
Although exactly the full breadth of differences, I'm not sure.
Okay, that makes sense. Yeah, which is why I tested like and, but apparently there's no and. So in some languages, and is short circuit and is not, or vice versa. But apparently that doesn't work. If that doesn't make any sense to you, don't worry about it. Short circuiting just means if you evaluate the first thing and it fails, you don't keep going. Right? So like you have multiple statements in your if, and if the first one fails, then of course the whole thing cannot be true. So there's no point in checking. But you can, in some languages, specify no, you still want it to check. Maybe there's something else. There's like a side effect that happens or something. So apparently the semantics for and the ampersand in Python are different. You could change that. So one of the things I probably won't talk about, you can actually overload operators in Python. So you could decide if you want, actually I have a nice example, maybe I'll show later in the week. You can define and to mean something totally different. And so one of the things that I'd like to show as a demo this last year is you can write your little package for reading in nifty images. That's actually basically just Nibabble, which is an existing package. But it just makes it so you can take two images and say image 1 and image 2, and it does a conjunction, right? And so the way you do that is really with like 3 or 4 lines of code. You just implement some new functionality that says when you see that and operator, it's supposed to do something other than what it would normally be doing. That's great, but it's also a little bit dangerous. It means that, you shouldn't do this as a general rule. Like, don't go around redefining like what the plus means. Bad things can happen. But it is really, really powerful when you're trying to define what are called domain-specific languages. So you have like some little domain you're working in where you want to just write some tool that really powerfully and quickly operates on entities within that domain, and you can use things like existing operators to. And so actually, one thing I suggested last year when I showed that demo, and it'd be great for a project this year too, is to actually implement something like that more generalized. So like take Nibabble, which how many people have worked with Nibabble or touched it? Okay, so quite a few of you, and just add a layer on top of it that allows you to do things like image 1 and image 2, or image 1 or image, right, and does implicit, or not implicit, but does conjunction, disjunction, these kinds of things.
So those changes would all be local, right?
Yes, so the way you would, so one nice thing about Python is, again, coming back to this idea that everything is an object, right? What's actually happening, I'm debating whether to just show you this now or, yeah, why not? I do want to emphasize I'm available this whole week, and if I'm going too fast or this isn't making sense, just and there's something you want, just track me down. I'm happy to talk about it. So I'll just, with that caveat aside, I will just jump to something completely different because I think it's kind of cool and since there's interest. Let me just find this. Where did my tips and tricks go? Oh, actually, I know where I have this. So this is, I thought I might talk about this, I probably won't, but if you want just a much more detailed take on, an opinionated take on why I think scientists should learn Python in most cases, you can find that in the Neurohackweek repository. But what I want to show you, just touching on the last point, is just this. So let's say we have this Nibabble library, and it has this nifty one object, and that is like a superb library that implements all kind of functionality for working with nifty images. What we're doing here is defining a new class called lazy mask, because it's just meant to do some simple masking stuff, and it inherits from nifty one image. How many people are familiar with inheritance in programming? Okay, so a few. So the idea here, this is it's not the most intuitive concept to wrap your head around. But the basic idea is you can think of this object nifty one image as, in some sense, being sort of, you can think of lazy mask as sort of a child of nifty one image that adds more functionality, right? So it's kind of like you took nifty image and you said, well, I'm just going to clone nifty image, but I'm going to add a little more stuff to it. I'm going to change the way it operates. And so we are basically inheriting from nifty image in this new class we're creating, but then we're adding a little more functionality. And in this case, literally all we're doing is adding two methods. Now remember, I told you in Python, you generally don't want to touch these double underscore methods, and you probably shouldn't initially at least, except for like maybe one or two that you kind of have to, like init. But you have a lot of power in these things. So what we're doing here is we're saying when someone uses the AND operator, so in practice what this actually means, there's a one-to-one mapping in Python between when someone types something like this, right? And when you do that, this looks to you like a simple logical operation, but actually it's not. What's actually happening is this A is the object that receives this function call, this method call, and this is the argument. So this is actually internally, it literally is being called like this. What you're actually doing when you do A and B is you're saying A and B, right? Everything in Python is an object, right? And these operators are basically methods on these objects. And so that's really powerful, because what it means is that now you can implement any semantics. You can have this and do anything you want. It's a method just like any other. So what are we doing in this case? We're saying, we won't worry about like the self and stuff. There's all these little details of object-oriented programming in Python we don't have to worry about. But what we're doing basically is we're just saying, we'll ignore this error. We're just checking to make sure that these images align and they can be actually combined. But really just in one line, all we're doing is we have, borrowing from NumPy, this logical AND. We're just taking the data from each image, and we are just doing a logical AND. So we're going to have a bunch of voxels here, a bunch of voxels here, and we're just picking out all the voxels where it's non-zero in both images. That's all that logical AND is doing. And then we're turning in a new image that's got just the non-zero values. And we do the same thing for OR, right? We're just defining a new semantics for the OR operator, the pipe, and we're returning a disjunction. So now it's going to return non-zero values, or return 1 actually, anywhere that the value is not 0 in either image. Okay. So hopefully that makes sense. And so now just to show you that this works, that's all it takes. Here now we're loading 2 images. These are in the repository, so this should run for you if you clone this thing. We're loading image 1, image 2, reading them in as nifty one object with this extra functionality, and then we say we want a new result that's image 1 and image 2, and I will prove to you that this works as intended. Now we're going to plot this, and this plotting takes a little while. But there you go. So the first row is the first image, second row is the second image, and here's the conjunction, right? And so you can do some pretty powerful stuff just by, I won't say hacking because it's the intended use, but just by working with these like double magic things. You can create essentially entirely new mini languages. This is not unique to Python. Ours I would say pathologically flexible. You can turn anything into anything in R. I think it's too flexible. It's very easy to do things that are confusing and cause problems. But you can build really nice tools this way just by judiciously kind of overriding some of these kinds of magic methods. But this is pretty advanced. I just wanted to show you as just to kind of give you the flavor of what is actually possible once you're proficient with Python. It's not going to be salient, I think, if you're just sort of learning how to sort of do data analysis in Python. For that, we can talk about Numpy and Pandas and all this good stuff. Any questions about what I just showed or anything related? Okay. Yeah, let me talk about data wrangling go. There we go. Okay, so let's talk about data wrangling. And so I'll stop talking about the basics, and I'll assume that the sort of basic programming stuff makes sense. If it doesn't, I'm happy to talk about it afterwards. What we're going to do here is we're going to work with some data, although it's just behavioral data, from the Human Connectome project. We have, let's see, about, what is the time? Okay, about an hour. And as I mentioned, the convention in Python is you start by putting all your imports at the top. There are some scenarios where you might not want to do that for various reasons. Most common reason being because the library you want to import is optional. Like, not everyone who uses the code needs it, and so you don't want to force everyone to have to install it. And if you put it at the top, then of course as soon as that file's read, it's going to try to import it, and it'll throw an error if it's not there. So sometimes you tuck away that import statement in code that will only be used at runtime. And so only people who need to have that installed have to worry about it. But here we're basically saying that, look, in this entire notebook, I think, plus minus, we know what all the dependencies are. And so that's nice, because right away you can look, just if you could tell just looking at this, if you know Python a little bit, you can sort of tell what's coming. You can tell, okay, look, they're going to be doing some numerical stuff. There's probably some data wrangling, because Pandas is imported. Regular expressions. There's some plotting in Seaborn, Matplotlib. Those are plotting libraries, et cetera. Right? So you get a sense very quickly of what you need. And it also tells you if you don't have some of these installed, now's a good time to do it. Okay, so that's just a kind of a general sort of indicators to what we'll be using. I run the cell, now we have all that stuff available. If you clone this notebook from GitHub and you try to run it and it fails, most likely it's because you have to install one of these things. And I don't know, for those of you who saw Dylan's presentation, I'm not sure if, did you, he's not paying attention. You can actually run commands on the shell with the exclamation there. And so if you find you don't have any one of these, you can very easily just do something like this. So let's say Seaborn's not installed. You can just run that, and that will actually, at a system level, try to install Seaborn. In this case, we have it. But so even from within the notebook, you can actually call system commands quite easily. Okay. So let's start by reading in some of this data. And so what we have here is the Human Connectome Project tasks are presented in something called ePrime, which maybe you may be familiar with. It's a horrendous, awful program, but people use it. And the behavioral data in the Human Connectome Project are all in this sort of format that comes out of ePrime. And they have this kind of naming convention. We're just going to read these tab delimited files. And there's a whole bunch of them. And so what we're going to do is just for every file in that set of files, if we want to know how many there are, we can. We are going to use Pandas, which is a sort of the workhorse data mining or munging library in Python to read it in. And I'll talk a little bit about this in a second. But just to kind of show that this works, it's basically behind the scenes looping over and over. And actually, so let me do this for just one file, just so you can see it in action. So we have these 200 files, right? And so let's take the first file. Oops. So the workhorse reading command is read._csv. If you're coming from R, it's very similar to read table. It sort of will handle almost any format you throw at it. And it doesn't just have to be CSV. You can actually tell it what the separator is, et cetera. It's probably poorly named. So we, let's say, take our first file, and we just say that the separator is a tab. Read CSV has a lot of arguments. So if you're in Jupyter Notebook, you can always see the signature by hitting Shift Tab within the parentheses. So you can see here, there's lots and lots of things you could pass to this. So odds are, if you have text data and you need to get it in and it's fairly regularly organized, some manipulation of these arguments will give you what you want. Of course, there's much more help if you want. So you can change the delimiter. You can do things like specify what the index column is. Maybe you have multiple header rows, or multiple sort of index rows, et cetera. All kinds of things you can do. So we'll just read this in. Oops. And now we can inspect this. And so we're just printing, and by default, Pandas will print, I think, the first 20 rows or something. I might have changed this at some point. And so this is what the file looks like. Right, so you've got your experiment name, HCP ID, this is the subject, I believe, run number, et cetera, et cetera. and lots of other stuff. There's, I think, like a couple hundred columns in these things, most of which are sort of junk we don't care about very much. And so all we're doing here is we're looping over this process. So for each file, we're reading it in individually, but then, because the subject, surprisingly, is not actually included in the context, so you wouldn't actually know which subject this is, what we're doing is we're extracting that from the filing. Remember I talked about regular expressions? Right, so here's one very simple example of where regular expression is useful in practice. You know that you need to add some data from the file name into the contents of the file itself. And what we're doing is we're searching inside that file F for this pattern, which basically says find 6 digits, right, exactly 6 digits, and that's what you want to keep. And that's just because nowhere else in these files, if you see 6 digits as subject ID, there's no other pattern set of 6 digits that we have to worry about. So. And then what we're doing is inside that data frame we just created, this one here, we're just creating a new column. And it's as simple as saying in this data frame object, create a new column called subject. So when you index with this notation, you index kind of like a dictionary. The convention is that refers to columns. And you're just setting a new value. Notice that you only have to set it once. So Pandas is doing what's called broadcasting, which is if you pass it a single value, but it has this data frame that has, let's say, 100 rows, well, on some level, like the knee-jerk thing to do would be to say, well, I don't know, I can't do this because you gave me one value, but I need to fill 200. But what it'll do is it's clever, and this is true of Numpy, which is the numerical library that Pandas relies on. It'll figure out, well, look, I can just repeat this value easily 200 times, and then it's the right dimensionality. And so it'll try to do what's called broadcasting and fill that in. And so that's nice because that means you don't have to yourself replicate this value 200 times. You can just pass a single value, and all the rows will be set to that value. So this is just to say, for each of these individual files, we want the entire column subject to have the value we just extracted. And then we're just appending that data frame we just created in each instance of the loop to a list that we're keeping there. So now we have a list of these 200 data frames, Pandas data frames. And finally, we're concatenating. So Pandas has this concat method that takes a list, and you have to specify the axis, and it's just concatenating them. So what's happening here, just to make it kind of more intuitive, right, is you have one data frame, and then you're concatenating another one, and another one, and another one. If I'd set axis to 1, that's going along the column. So maybe another kind of common scenario is you have different information, but it's from the same subject or something, the same subjects, and has the same number of rows. And so maybe then you want to stack these things going this way. So you have maybe like, I don't know, demographic information, behavioral data, et cetera. And so you can sort of decide how you want to concatenate them. And the point of this is when you run all this, if we now look at this data we've just created, it's going to look exactly the same because, of course, the top of it is just the first one, so it's literally identical. But now it has a lot more rows. Now going all the way down, we have 20,000 rows because it's all 200 files. And you'll notice that we have this subject. So I should have kind of done this first without, so you would have seen that subject thing did not exist. It comes out of the file names. We just added it. Okay, any questions about this so far, just reading in data? There's an equivalent write underscore CSV, which just writes out sort of equivalent. You can take a Pandas data frame and okay. All right, let's look at what we have and get a sense of what this data frame thing actually does. Actually, one thing I'm going to do here, since I probably won't need, just so I don't have to crane my neck, I will duplicate these display. Okay, better. All right, so the first thing we might ask is we want to know just how big is this data set we just created. And every Pandas data frame, and also every Numpy array, which again is the object inside this. So remember I talked about inheritance, right? So you can think of, well, this isn't really inheritance. You can think of Numpy as, in fact, I will show you. So what I'm doing here is just inside that data, that Pandas data frame object, there is a property called values, and that is always the actual, just the values of that table, right? So you can think of that table we just created, and if you just want the values of those tables without any sort of extra stuff from Pandas that lets us manipulate these things, so literally just the actual like numbers or text, then you can just call dot values. And what that gives you is actually a NumPy array. I mentioned that you could easily delete cells. Oh wait, I didn't delete it. Where'd it go? What did I do? All right, whatever. Okay. NumPy arrays will do all kinds of cool stuff. So in this case, we can look at the shape of this thing, and 20,000 by 126, right? So 126 columns, 20,000 rows. Maybe we don't want all these rows. So the first thing you often do when you get a data set that's particularly large and you know you're not going to need some of this is you slice some of it out, right? So you need just a subset of that data. So just like in MATLAB or R or any other sort of numerically oriented language, there's a sort of a certain syntax for working with subset or subsetting or slicing into n-dimensional arrays. In this case, a 2-dimensional array. And here's what it looks like in Python. The colon is basically code for everything. And so if we were to do something like this, and the comma separates dimensions, right? So you have 2 dimensions here, and so we need essentially 2 values. So what is this saying? What am I going to get back? Oops, not this shape, sorry. If I just do that, what am I going to get back? Right, all rows of the 4th column. Okay, all right. We could, of course, do more sophisticated things. We could say, well, give us all the rows from 50 until 100, and all like the 7th to 10th column. And of course, you can't really verify that this has the right dimensions. But if we look at the shape, 50 by 3, right? So that's just basic slicing, and there's all kinds of stuff that NumPy gives you out of the box. So for example, well, you notice that this is a string, and so let's just focus on these 2 numerical columns first. Actually, let's take the last 3 columns because they look like they're numerical. Nope, that's not good. I'm just trying to find numerical columns that I can actually do stuff with without running into problems. Well, this is a good opportunity to show you one other nice thing about pandas. So, sorry, let me just clarify then the relationship. And I know I'm jumping all over the place, but so you can think about the relationship between NumPy and pandas as sort of like the relationship between so NumPy is basically just a container for data that gives you a certain set of tools for operating on that data, mostly useful for numerical operations, so computation, things like taking means, standard deviations, matrix manipulations, so basic sort of mathematical operations typically on arrays of data. But what it doesn't do for you is a lot of what, for example, R will allow you to do with R's data frame, right? So if you are coming from R, you're used to, for example, columns having names and rows having names. So you can say, well, I want in R you can say, given a data frame, I want the column named name or size or something. And you can also name by row. That did not exist in NumPy, at least it didn't exist in a usable way. There are structured arrays, but they're kind of clunky, until pandas came along. And the idea is, let's take NumPy. It's a great data structure. It's very efficient. It's highly optimized. It's very fast. and just create something that wraps around that NumPy array, right? So it's still a NumPy array inside, but it's just wrapped with some extra functionality that allows you to do things like pick out columns by name and do all kinds of sort of data wrangling operations that make life much easier. And so in some sense, Pandas is sort of essentially it's like R data frames for Python, right? It adds a lot of the same functionality that exists in base R, if you're familiar with R. And so you have sort of very simple descriptive things like head, which shows you the first 5 rows, or the first n rows. You could also do the same thing with tail, right? So often you just want to get a sense of like what does the beginning of or the end of the data set look like. We have other descriptive methods like describe. And this is showing you for all the numerical columns, how many rows are there, what's the mean value, standard deviation, so just basic descriptive stuff. Not super interesting, but good to glance at most of the time. All right.
So the head and tail looks at the rows, right? Is there a way to look at the columns?
That's a good question. Well, so you could do something very simple like this, right? I mean, like so you have this T, which allows you to just transpose the dimension. So that's one way. It's a bit hacky. I think that's probably let's see. Let's see if the tail. So tail doesn't have the axis, so you could just do that, and that works fine. So there are often situations where you just want to transpose rows and columns, right? And so that you can do this in general. And so, Of course, in this case, it's not super informative because these are just like numbered subjects going down. But you could. And as with any Python object, remember, right? If you want to know all the things that the data set can do, then you could always just ask it, recognizing that you're going to have a lot here. So there's just tons of functionality built into Pandas data frames. One thing you'll notice is that because of the way Pandas structures are built, all the columns, these are individual columns, but they are now considered attributes. You can actually, I don't recommend it because it's confusing, but you can actually, if you want, refer to columns with the dot syntax. The reason I say it's confusing is because it makes it ambiguous, right? You then don't know if this is actually like a typical attribute of that object or if it's a column. So I would recommend, even though it's more typing, always referring to columns within these square parentheses. But just to come back to what I was saying, so we have just a ton of stuff that you can do with this data frame. And we'll talk about some of these things, but you can already see that there's going to be just lots and lots of useful things you can do with this. Was there a hand up? Any question? Okay. All right. So let's start talking about, so you have a data set, you looked at it, okay, it looks okay, nothing obviously jumps out at you. But of course, as with most data set, there's probably stuff wrong, and in general, lots of data has problems with missing values. These certainly do. I can tell you that these ePrime output files contain lots and lots of rows with missing values, and we may not want all of them. So I don't know or at the very least something. So one thing we can do right off the bat is we can say, look, we want to count all the rows that have. This I think changed. So I wrote this, I think, on an older version of Pandas. Pandas also evolves very quickly, which is good and bad. It's good in the sense that it improves rapidly, but expect your code to break occasionally, and typically just to make like small changes. So what I'm showing you here is just a sort of quick descriptive analysis. We're just counting up the number of rows that have, we're counting up the number of rows that have missing values for each of these columns, right? So we have, I think, something like 100 or almost 200 columns, and we're just kind of printing out how many rows have missing values. And we see right off the bat that most of these columns are essentially useless because there's like nothing in there, right? They're just like missing values everywhere. And then conversely, some of them have no missing values, which is good. That means we have sort of complete data. So that's just descriptive. We now know where the missing values are. And so let's say we want to only keep the rows that correspond to trials, because it turns out when we look at this, I can tell you that part of what's going on is the ePrime file consolidates all kinds of different events, many of which are not trials. And so we want to throw out all the rows that don't have actual like response data. And it turns out, if we go and look at these, that there's this procedure block variable or column in that file, and when the value is trials proc, that denotes that it was a sort of trial in the task. And so what we want to do then is conceptually, we just want to keep the rows that correspond to trials. We have this column procedure of the block, and it has strings in it, and when the strings are trials proc, that means that those rows came from a trial. And so what we can do, remember we talked about logical expressions, we can assign, well, let me take this step by step. So if I were to do this, right, what we're doing here is we're taking this column that we care about, and we're evaluating whether it's equal to trials proc. Now remember, again, right, this is weird because this is a column, but there's only one value. Same principle applies. It's implicitly broadcasting. So essentially what's going to happen is for every single row in that column, or every single value, in this case it's just one dimensional, it's going to check whether it's the same, whether it's equal to trials proc. And what's it going to do? Any idea what this will?
Check for the string, right? It's going to check for whether trials are proc.
It's going to check, so here we go. I'll show you what this looks like. So this is the column. These are the values. Just as an aside, another really useful little tool is value counts, which is basically a frequency count. So that's a really nice way to see. Okay, so most of these rows are these trial proc, but there's also these other things we want to get rid of. So I just showed you what this column looks like, and now we just want to keep the values that actually are trials proc, right? So basically, right. But so what is this going to return if I do this though? Because notice there's no assignment or anything here anywhere. We're not saying like keep only those rows. What is this going to get me back? Okay, and how many values?
The length of procedure.
Right, yeah, so does that make sense to people? So I'm going to get back, this is a single column in a Pandas data frame is a series. I'm going to get back another series that is just true or false based on whether that value at that position was equal to trials proc. So in this case, false, 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 true, 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 and you can verify that visually. You can see that, yeah, these are not, and then around here we start getting these trials proc, right? So okay, so that's great, but now we just have this series of false and true values. What good is that, right? That's not what we want. We actually want the rows from the original data frame. Well, the nice thing is what we can do is, well, so first of all, what we can do is we can store this. So we can say, let's keep this as our indexes, and that's just telling us for every row in that data set whether or not it had trials proc as the value at this procedure block column. But what we can do with Pandas data frames is something called logical indexing or Boolean indexing. And the idea is that if you pass, so remember how normally you would, remember how if you wanted like the fourth row in NumPy, you would do something like this, right? This does not actually work in Pandas. And can explain why. There are good reasons for it. This is actually what you would do. iLoc means integer location, so you're basically saying I want the fourth row. So normally, right, if you wanted just like to pull out just a subset of that data or set a subset of that data for that matter, we could also have done this equals to, and give it a new value. But one thing that's really nice in like NumPy and actually R and many other kinds of languages like this is you can actually index based on a Boolean array. Meaning you don't actually have to say, well, I want the fourth one, I want the fifth one, I want the 300th row, and pass the actual indexes. If you give it a vector or a list of values that has the same length as the whole data frame, then it will be interpreted as you saying for every single row, do you want it or not? And if it's true, it'll keep it, and if it's false, it won't, right? And so if you imagine now we have this data, how big was it again? We have like this, 19,200 rows, and we have this index, oops, I haven't actually run this. Oops. And I have this ends thing, which is just the telling us whether or not every row should be kept or not. We can actually directly index that. So we just say, well, data is now right? And so we're just setting this data variable to a slice of the same thing. And so, oops. And so now if you look at this data, well, you can't really see that from a glance, but you can take my word for it that we've gotten rid of all the rows that did not meet this condition. Right?
So, but then index would include both the X and Y information?
Yeah, so this is where, I mean, I'm sort of, so we should probably talk about Pandas indexing because it's a little weird if you're powerful. So the convention, it's true, right? It's very weird because like in this case, I've just told you this is operating on the rows, but if I were to do that's the column. So why is it that when you pass a string here, it's interpreted as a column, but if you pass in like a series of, or an array, it's interpreted as rows? To be honest, I probably should have changed the example. So you can, the data frame is two-dimensional, right? And so when you pass in one dimension, there's always going to be this question of, or when you pass in sort of like one value, there's always going to be this question of like which axis are you referring to? So, like, I guess what I would say is do as I say, not as I do, right? In general, you should probably get in the habit of not doing this kind of thing. Like even here, even if you just want one column, it's probably good practice to do this, although this I suspect will not work. And now we get into what's different about pandas. So in R, something like this would work just fine. And the reason is because in R, no care is taken to ensure that you're being sort of reasonable about what your column names are. And so, for example, you could name your column, or a row for that matter, 4, or even 0. And so then you would set up a situation where if I do something like, oops. I mean, let's just show you this directly. So we're going to define a new data frame. And we're going to say, okay, I just overwrote my existing data frame, so I'll have to redo that at some point. But I just manually created a little data frame. It has 2 columns. Notice the one is named 0. And so you might see where this is going. You can also name indexes. So I could say data index equals right? And so now if I have a row that's called 0, but let's say the first row is actually called 1. Okay. So you can see where I'm going with this, right? So if I did this now, if you could index just that was interpreted as the first row, what would happen? This didn't work, but let's say it did, right? What would you expect to actually see here? If I tell you I want the 0th row, or the row 0 and the column mouse, you have a problem, right? Or sorry, I should have said 1. Actually, that would be saner. It's ambiguous because in pandas, a nice feature is that columns can, and basically either columns or rows can have any value at all as their name. It can be a string, but it can also be a number. So you don't know if I ask you for this whether I want the first row, or sorry, the row with index 1, which is this row because 0, 1, or if I want the row with the name 1, right? So this is not actually a pandas problem. It's like a fundamental data problem. And if you want to be able to unambiguously pick out what you want. And so what pandas does, which seems annoying but is very sensible, is it really encourages you not to use this kind of indexing at all, but to use these much more verbose indexers. And there's 2 of them. One is loc and the other is iloc. And loc is location, so it's by name. And iloc is by index, so it expects integers. And so that's unambiguous because now what I can do is I can say I want this, and that gives me the value 5, which notice is different than if I had said iloc 1, and then I can't do mouse anymore because it's not a thing, so I have to give it the index, and that should give me a different value. Okay, so good practice in general is to use these things probably exclusively. When you want to refer to columns by name, you use location, and when you want to pull that by index, you use iloc. Okay, now let's come back to where I started, which is, so I could explain why. I mean, there's no real good reason for it. Indexing here, this is going to be taken as rows rather than columns, but really what I should have done just to remove ambiguity and avoid these kind of questions, which are good questions, is I should have just done this. Okay, a little more verbose, but clarity counts for a lot in this kind of domain, because it's very easy to screw something up, and often you'll assign things mistakenly, and then bad things happen. And so if we do this now, it doesn't work because I did something wrong. Let's see. Oh, because I reassigned. Yeah, thanks. Sorry, so I need to reread all the data in. So while we run this. Okay, still does not work. Location based on inversion type.
Ings is a series, right?
Sorry, yeah. So Boolean indexing only works for location. I'm actually not sure why that is. Because
outputs true when false strings are zeros and ones.
yeah, no, I think the reason it won't accept it for iLook though is because that could be interpreted as zeros and one, right? So Booleans can be interpreted as ints, I think. So we can see the general principle with Pandas is it tries to be very strict so that you cannot do basically the wrong thing by accident, but that means you're going to get a lot of errors. And the philosophy is just different from like R, where it's like R kind of assumes you know exactly what you're doing, you can't possibly make a mistake, and of course you make lots of mistakes. Pandas means you're going to have to correct your code much more, but it's more obvious when you actually screw up. And the downside is you write a little bit more code, you're more explicit. Okay, so this worked, and we basically just used that now, this long-winded way of coming back to this, but the point is we did all this to get this vector of true or false values, and because it has the same length as the data frame as a whole, we can just use it to basically select rows. So we're basically saying here, select the rows at these indexes, and we're passing this true or false, and what's going to happen is it's going to look at each of those values. If it's true, it'll keep the row. If it's false, it'll drop it. And so now, if we look at the shape of this thing, it should be smaller, and in fact it's down to 16,000 rows. So we've gotten rid of a bunch of rows that we couldn't use anyway. Okay, that's one way to do the query. It's a little bit cumbersome. It's not terrible, but it does mean you're kind of basically first setting up this variable temporarily of the indexes you want, and then you're using it to index the thing. Another thing you could do is use this query interface that's really helpful that Pandas has. And so this is sort of like if you've ever done any sort of SQL or database querying, it's very SQL-like. It basically lets you write a query string that operates over that data frame. So this is incredibly helpful. What we're doing here is we're saying, hey, data frame, data, we want all the rows where session selection list, so we're doing something a little different now, evaluates to or is equal to this. And notice we are actually specifying, we can actually pass variables in. So we define this variable SSL, but this is identical to just doing this. And so we could run that, and that would give you now all the rows where session selection list equals 3. Right? So this is basically a query that operates row-wise, and you can do much more complicated things. You can have ands and ors, etc. Basically any simple logical query. And so we could have written that, and you can, an exercise if you guys want, you can try to rewrite that query up there in this format. And the answer you actually will not be able to without a hack, which is that this query interface does not like non-alphanumeric characters, and so it will actually choke because of these parentheses. So you would have to rename this column and then do this, but it can be done. Renaming columns is not a big deal. And in general, actually, these kinds of things you probably don't want in your files. Naming is important. Like I would not leave this in. Probably I would rename that to something saner, like procedure _ block. Okay, so, all right. Now that's sort of a long-winded, actually before I get to the other NA. Okay, so now we have a sort of smaller number of rows. Let's say we want to keep only columns with more than one unique value. And I'm just kind of showing you there's no sort of, there's way too much in here to like do a comprehensive job. I'm just picking out sort of like things that I find myself often doing just to give you a flavor of some of the things you can do in Pandas. If you're coming from R, of course you can do all the same stuff. Think of this as just like learning the Pandas way. If you have not worked with either R or Pandas or some other language like this, then best case scenarios you're kind of blown away at how stuff that would take you like 50 lines of code to do in like native Python or Perl or something or Ruby can be done in like 1 or 2 lines, right, in one of these other kind of languages. So here what we're going to do is we're going to keep only columns with more than one unique value. This is a bit magic-y, so it requires some explanations. We'll take it line by line again. So let's take this line first. So what we're doing here is we're creating a new variable called number of unique, basically. And this is sort of pretty opaque, I think. So there's two kind of things we need to kind of look at here. One is this apply function, this apply, or method rather, that's called data frame. And what this does is basically take every row of that data frame and apply some function to it. That function can be passed in by name, so we could do this less confusing but more verbose would be to say this. Let's define a new function called number of unique. It will take as its input a row, which is actually a Pandas series, because any one-dimensional extract from Pandas data frame is a series, and we would return the number of unique values. So this is another nice method that Pandas series have. You can call n unique, which is the number of unique values. So I could have done this. Okay. And what this would do then is it would basically, for every row in that data set, apply this arbitrary function that I just defined. So you can have it do whatever you want. You can write any code in there.
No, it just automatically does it for every row individually, or?
That's what apply, yeah. So the default meaning of apply is applying over rows. You can also change the axis. So that's what this axis is, right? So 0 is rows. If you did that, it would apply to every column. So you have that flexibility. And there's some other stuff in there too I won't get into. And so you're just applying this arbitrary function. Python also has a simple way of defining lambdas, which are sort of, if anyone knows JavaScript, the closest you come to anonymous functions. They're much more limited, but the basic idea is you're defining a function that only exists temporarily within the scope in which it's created. So the idea here is it's not referred to from anywhere else. So that basically just ends up being equivalent to what I just showed you. So this is just saying, hey, data set, apply this function I'm going to give you, but instead of passing in some function that's defined somewhere else, we're right then and there defining this little function. It's called a lambda, basically. So it takes as input x and does exactly what we did before. So if this is confusing, don't worry about it. You can just write it out like I just did. I'm just kind of trying to cram a lot in just so you kind of see some of the things you can do. This is very helpful just when you're writing code quickly and you don't want to have to start writing these little methods explicitly somewhere else that are just going to clutter up your namespace and you're never going to need them again. So lambdas are helpful there. Only real problem, one problem with lambdas, they can only be a single line. So unlike some other languages, you can't have just like arbitrary chunks of code. You can only have like a one-liner basically. Okay, so that's that line, which just says count the number of unique values in every row or in every column. And the reasoning here is that, look, if a column only has the same value everywhere, it's probably just some constant thing that was set. We don't care about it, right? It's not useful to us. We probably won't want to analyze constant values. So let's identify all the columns that have at least one. So we counted for every column how many unique values they have, and now we're basically saying, very similar to what we did before. Now we're keeping as our indexes on the rows, we're taking this number of unique thing, and we're subsetting it, I can show you again step by step what this looks like. So again, the logic here should generally be to work from the inside out. So if you see something like this, so this kind of looks a little complicated, right? What is this doing? But if you think about this as, well, first of all, let me just think about what's going on inside this thing, right? So there's this expression n unique greater than 1. What is that doing? Well, that's just evaluating, again, for every row in that n unique, in that number of unique count, it's just evaluating whether there's more than one, with values more than 1 or not. And so now that we know that, now we can think, okay, great. So that what that means is that when we see this, we're now indexing into that thing we just created. So we literally just took that list of number of unique values, and we're now limiting it to just the ones that evaluate true inside. So we're keeping only the values that have more than 1. And then we just want the index, because if we do this, what we get back is the series. So this is the index and the value, but we just want the names because we're going to use that to select from our bigger data set. And so we can just get the index, which is the way of just getting these values. And so now we have just that index. And the last step is we now again use this location indexer, right? And now we're passing in, we want all the rows, but we want only the columns that we just extracted here, the names of those columns. And so this should now leave us with a much smaller data set that has a much smaller set of rows, or columns rather, and yes, so now we're down to 16,000 by 69. And so in really just like 4 or 5 lines of code, we've done a bunch of data cleaning that would be much more cumbersome if you were to do it in other ways. Okay, now all I'm gonna do here is rename columns so we can work with them more easily. Normally you would probably do this up top. And there's one other thing you could do. This is sort of the sort of industrial strength version of data cleaning, is just say, you know what, just drop all the rows where there's at least one missing value. Probably not a good idea in general, but if you know that anything that has any missing value is not valid, then you can. So this drop NA function is very useful. It will literally give you back only the rows that have no missing values at all. Again, you can change the axis, so you could make this keep only the columns that have no missing values. So if we do that, now we're down to let's see, I guess, right, because we've already gotten rid of the missing value. Sorry, so it won't change anything. But we could have, if we knew if we knew that these were the same columns, right, that all of these columns with these missing values were exactly the ones that have, what am I trying to say? If we knew that there were no columns that were only missing like 1 or 2 values, right, and we knew that all the columns we want to drop have just tons and tons of missing values, and there are no other missing values occurring anywhere, then we could have just started out by doing this and saved ourselves a lot of trouble. We would just said like any row that has missing value is gone. Okay, all right. Okay, so that's just very, very basic preliminaries, and now we're actually getting, in our last 15 minutes, we're getting to the point where we can actually start to like do some more serious data preparation, which would probably involve plotting. So one thing we can do very easily in Pandas, because it has built-in plotting, is we can start to plot some of our columns or variables, right? So here's reaction time. Remember, this just pulls out this Pandas data series. This is just the one column, but you can actually call plot on that, and you can immediately plot, in this case, the histogram. There are different kinds of plots you can construct, and in this case, we're saying we want 100 bins. So this is just very simple, descriptive. I don't generally use Pandas for plotting when I'm trying to create like a serious plot, but if you just want to get a basic sense of what's going on descriptively, it's often very useful not to have to import another library and start working with it, because you can just directly work on Pandas. So that's kind of nice. So okay, we notice here that there's something going on. There's lots of missing values. Well, they're not missing. There's reaction time values that are set to 0. Presumably that means no response, right? That's actually is what it means. Well, we don't want zeros, because 0, if we're like computing the mean, will completely skew our results. So we want to now replace these with missing values. Not a problem. This pattern should look familiar by now. We're first identifying all the rows where reaction time is 0, and then we're just setting for that reaction time column for those rows the value to numpy.nan, so that's basically a missing value representation inside NumPy, which is the numerical library this is built on. And so now just to verify, if we plot this, okay, great. So now those are gone.
In the previous slide of code, in the code.
Okay, this one?
Yeah. The absence of parentheses doesn't screw
the absence of parentheses. No, so for clarity, it's probably a good idea to do this, but the way this is evaluated is that basically the comparison is done before the assignment, or evaluation is done before assignment, so it would first look at this and then, but for clarity, it is a good idea in general, so I probably should have just wrapped that in parentheses, yeah. And sometimes there can be ambiguity, and so it's good to be clear, yeah. All right, so, okay. Now let's do something a little more interesting. So the structure of the data here is that you have different, this is working memory data, you have end back conditions, and you have different stimuli. So just to kind of, so we know what they are, I mentioned there's this value counts function, which is very helpful. So there's 2 back versus 0 back, and just think of these easy versus hard if you're not familiar with the end back task. And stim type, I believe there's like faces and words or something like that. Or sorry, faces, body, tools. These are images, and there's different categories of images. Okay, so now we're getting to sort of like descriptive analysis. Maybe we want to plot reaction times by the combination of n back condition and stimulus type, right? So it's a 2x4 design, and we want to very simply plot these things. Now we're going super high level. So there's this other package, and I'm showing this. This is really just sort of meant to show you the power of the tooling, as opposed to like what I'm going to show you could be generated with a lot of Python code. It could be generated with more matplotlib code, et cetera. But if you have sort of a well-defined question like this, often there's a plotting package that will do exactly what you want. And in this case, there's a Seaborn package that has this facet grid construct, which is quite nice. And what you're doing here is basically constructing a grid that's faceted by certain dimensions, and it's expected Pandas data frame. So that's what's nice about this whole ecosystem, right? It's sort of, it's not as nice as R in the sense that in R, out of the box, everything sort of is one integrated language that works with everything. But we've now moved to a point where even in Python, even though these things are created by different people, et cetera, and they're all independent chunks in some sense, most everything now in the data environment depends on Numpy and Pandas, and so you can generally expect things to know what Pandas data frames look like. Seaborn certainly does, and so we pass in that data frame, and we're now specifying that we want the column of this grid to be based on n back type, 0 versus 2 back, and the color or the hue to be coded based on stimulus type. And that just creates, if we just call that one line, it doesn't do anything, but now we can map that to a particular column that actually has the data. So this is really, without this second line, this is just an arbitrary sort of abstract structure that says we're going to set up a grid defined by these two dimensions, and any value, any column you pass me is going to get basically plotted based on that structure. And so we pass in the name of a column. We also can specify what kind of plot we want, because nothing about this structure says what type of plot it is. It doesn't say whether it's a histogram or a scatter plot or what. So we're just setting up this gridding structure basically, and then we can ask for a kernel density estimate plot, which is basically a smooth histogram, and there we have it. Right, and so now what is this? Well, we have reaction time distribution for the 2 back condition and the 0 back condition, and the colors are the different stimulus types. So
it's really cool when it actually matches the axes when both plots and plots.
Oh yeah, and I think you can turn that on or off, but by default I think, yeah, I think that's the case. Let's see. So yeah, so you have to see these share y and share x arguments. So they're on by default, but you can turn them off. So you might decide, well, I just want to maximize the range of my axes for each of these things. So you have control over that. And the way to think about this in general, and this is, if I do a visualization one, I'll kind of emphasize this point. The downside of the Python visualization ecosystem in particular is it's kind of scattershot. There's all kinds of different packages. And some of them are not very good, some of them are great, but they're not super intuitive. But what's really nice is that almost all of them depend on something called matplotlib, which is sort of the workhorse plotting library, which is very low level but very robust. And then people have just started writing sort of layers on top of that, right? And so unlike in R, where you can think of most of the packages being, they take control over the canvas, and they control the canvas, and that's it, right? So you're limited by what that package can do. If you're using a plotting library that's built on matplotlib, everything is really just constructing. Remember, everything is an object, right? Including plots and components of plots. It's just constructing, in some sense, a set of instructions about what's going to happen when you actually draw this thing. And what that means is you can take the Seaborn package, you can generate this plot, but then you're actually still working internally with matplotlib objects. So if I really wanted to, I could actually say, look, I don't like the color of this line. I'm going to reach in there explicitly, find that line, and change its color manually. Well, manually, like in matplotlib code. So that's nice, because it means that you can start off with a very simple, fully automated type of thing that does more or less what you want, and then you can start tweaking the exact appearance and so on. You don't have to sort of sacrifice power for this kind of flexibility, or for speed, I should say. Okay. What else can we do? Let's see. Probably nothing, because we're out of time. So, I mean, one kind of thing you probably take away from this, and of course this is going to be true for any programming language, there's far too much to cover in like 2 hours, right? So I've tried to cover like a little bit of different things. I'm happy at any point in the week if you find like 3 or 4 people who want to know more about visualization in Python, just come grab me. I'm happy to we can just walk into one of those rooms, and I'm happy to talk about visualization. There's plenty of other people here, and one of the reasons for working in Python, we kind of wrote this on the GitHub README as well. You guys should feel free. I don't think Errol mentioned this, so I'll mention this for the people here. You should feel free to work in whatever language you want, right? But one of the things that's nice about Python is there's a lot of people here who do all or almost all their work in Python, and so that's one benefit. And if you have questions about really any part of the Python ecosystem, come ask me or ask Ariel, and we will find the person who knows probably better than anyone in this room at least what it is that you want. But this hopefully gives you at least a bit of a sense of like the flexibility with which you can analyze data using pandas. If you're coming from R, again, this is sort of just giving you sort of a mental model of like the translation between these things. The biggest difference will be that R is very functional, and you probably notice that here almost everything is sort of like methods called on objects. People prefer these, you have preference, that's fine. There's no right answer here, it's just what you like. Any other questions about any of this? Anything I've talked about or not? Python in general? JB, any comments?
Dinner time.
Dinner time, okay, that's good. All right, thanks.